Hi. Let's start discussing induced norms now. So let's look at the definition. The basic idea of induced norms is, before looking at the definition, by induced norm, what we mean is induced norm is a matrix norm, which is induced by a vector norm. We have a vector norm, and if we have a matrix norm which is actually induced by this vector norm, then it's called an induced norm. So the definition of induced norms is, let this function be a vector norm on Cn. Then matrix norm on space Cn cross n is defined as matrix norm of matrix A is defined as max of norm x equal to 1, norm of Ax. So what does it say? It's similar to it's not exactly the same, but similar to what we had for dual norms. Okay, so to find this matrix norm, we have a vector norm already defined. We have to solve this optimization problem. We have to say search over the set of feasible points which have x is equal to 1, and then find Ax for all such x's. The maximum value of that Ax, norm of that maximum value of Ax will give you the induced norm or the matrix norm. Yeah, this is how it is defined. There are also multiple ways of modification which can be done. So as a note, remember for matrix norm, even though we define it as y transpose x, we also ended up writing it as modulus of y transpose x by like some modifications. In the similar fashion, we can also modify the definition of induced norm. Matrix norm of A, which is the induced norm, is we've already seen it as max of mod x is equal to 1, norm of Ax. But this can be also written as max of x greater than or equal to 0. Sorry. This can be further relaxed, like norm of x less than or equal to 1, norm of Ax. Why is this so? See, suppose we look at all the case of x's which was actually less than 1. Okay, I mean, let's take a 2D case where we have something like an L2 norm. Okay, so right now we were just looking at all the points in this particular circle, unit circle, right? But even if you add those interior points, and let's assume that there we have a maximizer which maximizes this function, and it happens to be in the interior of the circle. Okay. In that case, what we can do is, okay, let's try to do this more systematically. Let's say we found an x hash, norm of x hash such that is equal to b, which is less than 1. Okay, which is actually a maximizer of this. Okay, then its corresponding maximum value is norm of a x hash, right? This is the its corresponding maximum value. But we can scale this x up, right, to come to 1. How do we scale it? We can scale this x by 1 by b, so that this x will lie on this. By the property where b is a value which is less than 1, so 1 by b is a value which is greater than 1. So by the homogeneity property, even if you scale it by this, the value of this ax, new value will be 1 by b times modulus of 1 by b times ax star, which will be, of course, greater than any value which is more than the maximum value which we've already formed. Why? Because 1 by b will be greater than 1. And if you multiply a positive quantity with a value greater than 1, the resultant value will be definitely greater than the initial ax hash which we had. So even if you find any value which is less than 1, you can actually scale x correspondingly and try to get, we can get the corresponding x which is actually on this circle, or which satisfies this condition. Okay. Because of that, you can also include all the points which are actually in the integer. It doesn't matter. You can relax this condition a bit, and still the max value won't change. Also, here, this is for the unit norm vector x. You can further modify this optimization problem by writing for all x, we slightly modify the cost function. If you take an x and modify this function like x by norm of x is anyway, for any function, x not equal to 0, x by norm x is equal to 1. So you can modify this function like this and take norm x outside. Max of x not equal to 0, norm of ax divided by norm of x. So if you modify the cost function, this is also another way of expressing induced norms. Further, we have also written here that this is equal to 1 ax by x. But in fact, this need not be the vector norm. This could be any vector norm. Why? Because of the equivalence of norms. Even if we are assuming that by convergence it takes another equivalent, by convergence it converges to 1 norm. It will converge in terms of another norm. So this is max norm of x. Alpha is equal to 1 of ax by x. I'm not sure how frequently we'll be using this definition, but I think all these definitions are actually valid for a matrix now. Okay. Yeah. Let's look at. So this is how we define matrix norms. So the theorem says if we define a function like this, the function is a matrix norm. 1. 2, it satisfies this inequality. Matrix norm on C and cross N. 2, it satisfies this inequality, which is similar to what we had as a submultiplicativity property in terms of product of two matrices. Okay, is less than or equal to matrix norm of A times vector norm of X. For all A belongs to C and cross N, and X belongs to C. Also, if you have such an induced norm, the induced norm of identity matrix is always equal to 1. We've already seen that for any matrix norm, uh, the matrix norm of I is greater than or equal to 1. But if it's an induced norm, then its value is specifically equal to 1. So let's try to prove this, prove these statements. Proof. So we have to first prove that this function is actually a norm, a matrix norm. For proving that it's a matrix norm, we have to prove all these properties. One is non-negativity. So we know norm of A is the max. Max of norm x is equal to 1, norm of AX. So how this is always greater than or equal to 0. This is always since it's a vector norm of AX is always greater than or equal to 1. And max of non-negative numbers is always greater than or equal to 1. So this is proved. Second is 1A. If norm of A is equal to 0, we have to prove that A is equal to 0. Can we prove this? Norm of A is equal to 0 implies max of norm of AX is equal to 0, which means AX is equal to 0. For all x, if and only if A is equal to 0. How do we prove this? X, we have x not equal to 0, right? Even if we have x not equal to 0, let's look at one of the ways to prove this is let's take x as e case, like 1, 0, 0, this is 1x, x2 as 0, 1, etc., 0, etc., xn as 0, 1. And if you multiply a with x1, you end up getting first column, right? Of similarly, a of x2, you end up getting second column. And all these values are in fact 0, which means that a has to be 0. So we're just looking at specific like n vectors which are feasible solutions, which form the feasible set. And from those equations, we can formulate that A1 will be equal to 0, A2 will be equal to 0, etc. A n will be equal to 0, which implies A is equal to 0. And if A is equal to 0, then X is obviously equal to 0. The other way we can prove that easily. So 1A is also proved. Now we have to prove homogeneity. So we have to find norm of CA, which is in fact equal to max norm x equal to 1, norm of C AX. Right? This is in fact CX is a vector. So the AX is a vector, and of course, it's a vector norm. So that vector norm satisfies homogeneity. You can take this as max of C norm of AX, mod C into C of AX. You've already seen it's a positive constant into max of a positive constant into a positive quantity. You can take the positive quantity outside. that is C into max of norm of Ax equal to 1, norm of Ax. So this is same as into matrix norm of A. So hence homogeneity is also satisfied. And we have to prove triangle inequality. Triangle inequality. To prove triangle inequality, it's also not very difficult. We have norm of A plus B, matrix norm of A plus B is equal to max norm X is equal to 1, norm of A plus B times X, which is in fact equal to max norm of X is equal to 1, norm of AX plus BX. So this is actually the max of a quantity, sum of a quantity is always upper bounded by the individual maximums, sum of the individual maximums. So this you can write it as max of AX plus max of norm X is equal to 1 BX. This is again is equal to norm of A plus norm of B. Matrix norm of A plus matrix norm of B. So this is also easily provable. Now we have to do some multiplicative, which is slightly more tricky. Not too much, but it is slightly use an alternate definition, activity, to prove this. Okay. So this is norm of AB, product of AB, matrix norm of AB. So here we use the definition where we have X by mod X. So this is max of X not equal to 0, norm of ABX divided by mod X. And this is okay. Yes. This for this actually we can use we can multiply, divide and multiply by bx. Norm of a bx by norm of bx, norm of bx divided by norm of x, where bx is not equal to 0. So this is max of product of two numbers. This is in fact less than or equal to this is in fact equal to bx is actually another vector y, and x is so we can actually replace this, which is max. This we can replace the y, and x is not equal to 0, bx not equal to 0. Can you see that bx not equal to 0? We've already seen. So in this definition, this is matrix norm of A into matrix norm of B. But I'm not really sure why this inequality holds, because I have max of, let's try to understand this, max of A into B. Okay. Both are positive quantities, right? It's a vector, right? So A into X will be again a vector. Max of that vector norm. Okay. Yeah, that is actually true because see here we have two individual vectors. If you multiply, take the norms of them and multiply. Okay, let's try to understand this. Right. We have two vectors x and y. Okay, so we're trying to find max of x into y. X into y being a norm of x into norm of y. So you take some random norm, you find the norm, and you take the norm. Uh, these are indeed two positive quantities. You multiply them, uh, then take the max out of it. So let's say this is giving a value like 5. We have a vector like 1, 2, 3, and we have another vector like 2, 5, 7. And let's say we are taking infinity norm. Okay. Now this infinity norm value will be 3 here, and this will be 7 here. So 3 into 7. This is one vector. We have another vector. Okay, understood. So we're taking yeah, we have multiple vectors. This is one vector. So yeah, okay, let's understand it like this. For the candidates of X, we have multiple vectors like 2, 3, 7, 1, 5, 8, 2, 9, 12. Okay. And for Y candidates, we have 1, 1, 2, 3, 7, 2, like that. We have multiple other candidates. What we're trying to do is here we find the, let's say we are taking the infinity norm. So here it will be 7, here it will be 8, here it will be 12, here it will be 2, here it will be 7. Let's say we have another 2, 7, 8, 10. Here it will be 10. Okay. So in this step, what we're trying to do is we take the product of all these combinations, like 7 into 2, 8 into 17, 12 into 10. Okay, and then take the max. Fine. The other one is we only take the max of it. Like here the max is 12. Here the max is let's say 10. Then 120 is the highest value. But there are also other products. So 120 will be always the highest value. Hope that is clear. So whether this inequality is actually true. This is true. Max of two norms is always less than equal to max of the first norm and into the max of the second norm. This is actually true. Fine. So we proved that this is also true, and which means that all the conditions are satisfied. But also we have to, there's a detail here. If bx is equal to 0, then abx is equal to 0, right? If abx is equal to 0, and of course its value will be a minimum, right? It can't be a maximum. It can't be a maximum. So x can be safely discarded. Won't be a candidate, which is actually relevant. Fine. Now let's look at the next property. Now we have already proved the first part. Now let's look at 2. 2, what we have to do is we have to prove that norm of A into X is less than or equal to matrix norm of A into matrix norm of X. sorry, vector norm of X. Proving this is actually simple. We have AX by norm X is less than or equal to max of X not equal to 0, norm of AX by norm of X, right? Because this is one value and the maximum value will always be greater than this quantity. But this is actually the matrix now of A. So AX by norm X is less than or equal to matrix norm of A implies norm of AX less than or equal to matrix norm of A norm of X. Right. This is also proved. Now we have to prove that for induced norms, matrix norm of I is equal to 1. How do you prove this? Ix is equal to max x not equal to 0, norm of Ix divided by norm of X. Right? So max x not equal to 0. This is Ix is actually x, norm of X, by norm of X. This is max of 1, which is equal to 1. This is also proved. So all these things are proved. Now, yeah. Also, this is also known as, the induced norms are also known as operator norms. Or there's also another name, which is least upper bound norm. Upper bound norm. Okay. Let's end the discussion of induced norms here, and in the coming lectures, we'll look at few examples of induced norms.